So I shaved this morning, Wayne.
Oh, I could do with a shave.
Yeah. You know, hair is made by amino acids and proteins.
Yeah, of course it is, yeah.
Why cutting the protein chain in half?
Ah, what you've done there is you've not understood.
Ah.
I guess really you're sort of cutting some sort of chain somewhere, I guess, but no, you're not. No.
Rats, but can we do that? Can we cut the protein chain?
We can indeed, and it actually cuts at a specific point every time. That's the difference between shaving. That's why it doesn't really make sense.
I see. Okay.
Okay, so we can in fact do it.
We can break chains, but first, we need a chain, right?
Yeah, so first we'll talk about forming them before we talk about destroying them.
Yes. So we need 2 amino acids.
Yep, if we do 2 different amino acids, it will explain a point in just a second.
Yeah.
We'll do simple ones.
So we have glycine, which is our first one again.
Yep, so the central carbon just has a H.
And say the residual group, and the other one being CH3, so this is alanine?
Alanine, or alanine, whatever.
Yeah.
So these are just 2 amino acids, and they can bond together. Now, each of the amino acids is a peptide. If you bond them together, you're going to get peptide chains. Now, when 2 peptides join, that's called a dipeptide, which is 2. 3 would be tri, 4 would be tetra.
Maybe, but you go on to poly from 3 and above, really.
Yeah. So 2 is di, after that poly.
Yeah.
So I mentioned that because those are some words you need to know.
There are, and they form together by a condensation reaction. If you don't know what that is, you form water at the end.
Imagine the condensation on the window, you know it's water.
Yeah.
You have to take out water.
So we have a water there, and that's why we take it out.
Yep, so this carbon's going to be bonded to this end, so it's going to go on. That's why it makes sense to do that.
But why the order of, in this particular example, the order matters. It could happen between these 2, or it could happen between that one and that one over there.
Yeah, so if we do a dot 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 there, and then dot 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 here. If you draw that as a chain, it's going to look different if it's that way round.
So in an exam question, look carefully in the order they've written it and how they've written it, because that'll make a difference.
Yeah, because if you imagine a really, really long chain, it definitely matters which one, because if you rotate it, they're not the same thing. So make sure you keep an eye out. And that would form a dipeptide.
And now we have a chain, we should break it.
We should break it.
Alright, so write up the full chain again.
So this C is just going to be bonded to that N, so I can keep this bit and rub out this bit and redraw it as connected. So that C, as I said, is now bonded to that N because we've removed the water.
Yeah, and then the rest is normal.
Yep, and we're still going with its alanine or alanine, CH3.
So we break up these chains, and in the middle it's a peptide bond, you need to know that as well.
Yeah.
This is just a peptide now, it's a chain, not an amino acid.
Yep.
Break it by adding water.
And we're going to add it where it connected, so at this point here is the part that's going to break.
But there's 2 different ways of doing that, isn't there?
There is, there's an acid and an alkaline way. I think we'll go through the acid first.
Yeah. So acid and alkaline.
There's conditions for each that you need to know. They're not horrible like some other conditions you might need to know, but there is conditions, and we need to talk through. It's not quite a mechanism, but it's the idea of what's happening.
Yeah. So start with heated under reflux.
Yeah. So reflux is important.
Yeah.
The acid has to be very concentrated.
You have to do it for quite a long time as well.
About 24 hours to properly break it up. And we use the idea, you don't do it really concentrated over 24 hours, but we use the idea when we marinate chicken.
Yeah, you add a marinade, which would be slightly acidic, and it'll break some of the bonds, making it more tender.
Yeah. That's good. Some people use vinegar, some people could use other slightly acidic things, whatever. But it's used, the idea. In chemistry, we're going to do it properly.
Yeah, we're going to do it now, and we're going to do loads of it, so we need to do quite hardcore conditions.
So we've got the acid, but rather than writing the whole acid, the only important part is what it donates, the proton.
The proton, so we've done that.
And it's also in water, because we need to break the bond to start with, which means doing it in reverse.
Yeah, so we need to break the bonds, and we need to get it back to what it was to start with. So the OH goes to our carboxylate bit.
Yep, so the glycine is going to actually look what it looked like to start with.
Yeah.
And that's what you need to remember. So it's now going to be O to H. So this bond is now broken, so this is a thing, it's back to its original state.
Yeah. Then
we've got this one, what's left is that, because this is now broken, this is where the water's been forced in. That's called hydrolysis, when you force water in.
We've still got an H remaining from our water, and that goes on to here.
But if we leave it in this, in this form, what could happen is these could just bond together and make another condensation reaction, taking us right back to this.
No, it won't. And we'd have that under acidic conditions, so what's it going to do when?
Well, it's donated a proton, and this place can actually receive a proton and become positively charged. Remembering your Zwitter ion, this is not a Zwitter ion, but remembering the theory of the Zwitter ion, it can receive the proton. And when it's like this, if it was to do a condensation reaction and take out this OH, you'd have an ion in the middle here, and that doesn't really make any sense. I don't think that would be very stable. So this makes it, or probably makes it so it can't go back.
Yeah. So not only can we do it under acidic conditions, we can also do it under alkaline.
Yep, so we're going to keep the original products but rub off all of these steps because
Okay.
they're not right for the alkaline.
And the last bit, and for alkalis, you just do it under 100 degrees. It does work a bit differently, I guess a bit simpler.
Yeah, this one's a bit easier. So what we're going to add is sodium hydroxide, or A hydroxide,
Yeah.
we're going to use this one.
No water in this case.
And it doesn't quite do what you'd expect.
So you'd expect the OH here to just bond, like it did before, to the carboxylic acid group, and it doesn't quite.
It doesn't, and that's what you've got to remember. Rather than making the first one a normal amine that it was before,
Yeah.
it does the jazzy salt, which means there's going to be some sort of ion, and it's here where it would be an OH.
There it is.
It's actually breaking.
Yeah, it's breaking there. I like to think of the alkaline one is the bit that affects the carboxylic acid, and the acidic one affects the base thing, which is then the amine.
That's a good way to think about it. So then what we're going to have
Is what we'd have normally.
yeah, so we've got the N bonded to the H because this bond again is broken, it's the same bond being broken. Then we've got the rest of it's unchanged, that's not going to be affected. So we've got all the rest of it the same, and this bond, there's an H left over to bond to it. And again, because this is O minus Na plus, you can't do a condensation reaction to take it back to the original thing, so it's irreversible, which is probably what you'd want if you're doing this.
Yeah, which is pretty handy. Alkaline less when you have chicken, you don't want to put that sort of thing in your chips.
No, I would not put that on my chips.
But, polypeptides.
Ta-da! So, we'll go on to the next video now and see you there, I guess.
Alright.